Hello everyone, my name is Asmita Surve and my roll number is 232. Today I am going to explain the Weiss theory of paramagnetism. As we already studied the Langevin's classical theory of paramagnetism, this Langevin's theory failed to explain the complicated type of dependence of susceptibility upon temperature. The Langevin's theory also does not explain the relationship between paramagnetism and ferromagnetism. Later in 1907, Weiss introduced the first modern theory of magnetism, that is molecular field concept. The Weiss also assumed that the internal molecular field of paramagnetism is directly proportional to the magnetism. Weiss assumed that the internal molecular field Hi is directly proportional to the magnetization. Hi, internal molecular field Hi is equals to lambda m. Give this as equation number 1, where lambda is the molecular field coefficient or constant and m is the magnetization. Then the external field H acts on a dipole. Then the net effective field is given by H of E. Net effective field is given by H plus H of I, that is H plus lambda m. Give this as equation number 2. Net effective field is H plus lambda m. According to the Langevin's theory of paramagnetism, we know the magnetization upon saturation magnetization is equals to the Langevin's function. Rewriting this equation, m is equals to m of s, L of A, Langevin's function is equals to A by 3, where A, we know the formula for A is equals to mu m b upon k b t, for A is less than 1, and ms saturation magnetization is equals to mu m n. The factor mu m n is called the magnetic moment per unit volume when all the dipoles are aligned in the direction of magnetizing field m. Then put this value into this equation, we get magnetization is equals to mu m n into A is equals to mu m b upon 3 kb t. We know the formula for magnetic field B is equals to mu naught H, applied magnetic field H. Then effective magnetic field BE is equals to mu naught HE. Put this BE into this equation by considering B is equals to B of E. Then magnetization is equals to mu m n into mu m mu naught H of E upon 3 kb t. Then magnetization is equals to mu m whole square n mu naught upon 3 kb t. Then H of E, from equation 2, put the value of H of E as H plus lambda m from 2. Then magnetization is equals to this. As we know, according to the Langevin's classical theory of paramagnetism, we know the formula for magnetization m is equals to mu m square n mu naught H upon 3 kb t. Put this formula into that equation, then we get magnetization m is equals to mu m square n mu naught upon 3 kb t H plus lambda mu m square n mu naught H upon 3 kb t. Then magnetization is equals to by taking out H common, we get mu m square n mu naught H upon 3 kb t 1 plus lambda mu m square n mu naught upon 3 kb t. After that, taking this at the denominator, we get mu m square n mu naught H upon 3 kb t 1 minus lambda mu m square n mu naught upon 3 kb t. As we know, the formula for magnetic susceptibility psi is equals to magnetization upon applied magnetic field H. Then put the give this as equation number 3. Put the equation 3 into that magnetic susceptibility, we get psi is equals to mu m square n mu naught 3 kBt H upon H 1 minus lambda mu m square n mu naught upon 3 kBt. Then by cancelling out H, we get magnetic susceptibility is equals to mu m square n mu naught upon 3 kb. Multiply this t to the whole bracket, we get t minus lambda mu m square n mu naught upon 3 kb. And then psi susceptibility is equals to mu m square n mu naught upon 3 kb t minus theta. And susceptibility psi is equals to mu m square n mu naught upon 3 kb t minus theta, where theta is this whole term we consider as the theta is the paramagnetic Curie point. Then susceptibility psi is equals to C upon T minus theta. This equation is known as Curie-Weiss law, and where C is the Curie constant. C is equals to Curie constant, and we know value of Curie constant is mu m square n mu naught upon 3 kb from Langevins classical theory of paramagnetism. Curie constant C, and T is the absolute temperature in Kelvin, where theta is the paramagnetic Curie point or Weiss constant theta, and here we write the theta term as lambda mu m square n mu naught upon 3 kb, and we know this term as a C, Curie constant. So C lambda is the paramagnetic Curie point or Weiss constant, is a measure of strength of interactions theta. Then this term susceptibility psi is equals to C upon T minus theta is the Curie-Weiss law. After that we see the two situations. First is for the temperature T below the paramagnetic Curie temperature, means temperature T is less than the paramagnetic Curie temperature theta, then the susceptibility becomes negative, and for most of the paramagnetic materials this Curie temperature is quite low, so this situation is rare situation. After that, second situation is for the temperature greater than paramagnetic Curie temperature, means for the measure of temperature above the paramagnetic Curie temperature, then susceptibility of course is positive, and ferromagnetic substance becomes paramagnetic substance. Then we see the graph for paramagnetism and ferromagnetism. For paramagnetism, we see the susceptibility psi versus temperature in Kelvin. Susceptibility psi versus temperature in Kelvin. We know formula for psi is equals to C upon T. For this formula is for Curie law, and we see the graph as this curve. And for ferromagnetism we get curve for susceptibility psi is equal psi versus temperature T, as the here somewhere is the theta, and this is the curve for ferromagnetism, and formula is psi is equals to C upon T minus theta. Here T is greater than theta. Then ferromagnetic materials behaves like a paramagnetic materials. This is the relationship between paramagnetism and ferromagnetism. After that we will see the Curie-Weiss plot. This is the Curie-Weiss plot. So see, this plot is for Curie law and this is for Curie-Weiss law. For Curie law, molar susceptibility psi m inversely proportional to the temperature T, as we see the Curie law. This is the Curie law. The plot for molar susceptibility versus temperature, we get this curve for Curie law curve, and C Curie constant is equals to the inverse of the slope from the graph we get. Then we see the Curie-Weiss law. For Curie-Weiss law we see the inverse molar susceptibility versus temperature. The plot for inverse molar susceptibility versus temperature is called Curie-Weiss plot. Ideally the plot should be linear. Then from the graph we can extract the Curie constant C by taking the inverse of the slope, and theta, Weiss constant theta, is equal to the x-intercept. From the graph we get this value. Then the sign of theta tells us about the short range of magnetic interactions. Means if theta is 0, then substance becomes paramagnetic substance and spins are independent of each other. If theta is positive, means greater than 0, then substances are ferromagnetic substances and spins align parallel to each other. If theta is less than 0, means theta is negative, then substances are antiferromagnetic and spins align antiparallel to each other. These two graphs are Curie-Weiss plot for paramagnetic materials. After that we see the Curie law and Curie-Weiss law. For Curie law, the Langevin's theory of paramagnetism, which leads to the Curie law. Curie law is based on the assumptions that individual carrier of magnetic moment do not interact with each other, but they are acted on the applied field H and the thermalization. And this is the formula for Curie law, as susceptibility psi is equals to C upon T, inversely proportional to the temperature. And then Curie-Weiss law, for most of the paramagnetic materials, obeys this Curie-Weiss law, as susceptibility psi is equals to C upon T minus theta, by considering the interaction between the elementary moments. Weiss assumed that this interaction could be expressed in terms of fictitious internal field, that is molecular field Hm. Then these two relationship, that is paramagnetic and ferromagnetism, we will see. Then Curie-Weiss law for paramagnetism. This is Curie-Weiss law of paramagnetism. The two graphs, that is for, if suppose susceptibility psi, here origin 0 versus temperature T, then we get the curve as like this, means decreases, means susceptibility psi is equals to C upon T minus theta. We get this as a curve. For inverse of susceptibility, means 1 by psi m versus temperature, we get linear curve, means increases like this, and here is the slope, that is 1 by C Curie constant. Means psi m is equals to C upon T minus theta, and 1 by psi m is equals to 1 by C T minus theta by C. For inverse of molar susceptibility versus temperature, we get the linear curve for graph. So that's it. Thank you so much.